Good evening. I'm Chuck Blumenfeld. I'm the Executive Director of the University of Washington Alumni Association, and I want to welcome you all tonight to this engineering lecture. Engineering the Best, Boomers, the Bridge, and Boeing 787. This is the second of a three-part lecture series. This lecture series is a partnership between the Alumni Association and the College of Engineering. It's part of the Alumni Association's lifelong learning program that brings educational programs featuring prominent alumni and faculty at the University of Washington. Tonight's talk promises to be a fascinating one, particularly to anyone who has had to drive to and from Gig Harbor over the Narrows Bridge. Approximately 90,000 people a day use the bridge. In July, the new Narrows Bridge opened. To Washingtonians, specifically engineers, the Tacoma Narrows has been a symbol of failure, with the infamous 1940 bridge named Galloping Gertie, which collapsed in high winds just 129 days after it opened. To quote the project manager, the new bridge may be the redemption of the Narrows Bridge. Tonight's lecturer is one of our distinguished alumni. Steve Hansen is Senior Vice President of the Kiewit Corporation, one of the primary construction contractors for the new Tacoma Narrows Bridge. Tonight he will give you an in-depth engineering story of the bridge, end-to-end, tower to the bottom of the Narrows. Joining him for the presentation is our own Joe Mahoney, Professor of Civil Environmental Engineering. Please join me in giving a warm welcome to Steve and Professor Joe Mahoney.
Thanks, Chuck. Good evening. Let's get started. Again, I'll say a few things. We've done 3 bridges at the Narrows, a very challenging location, about a mile across. And of course, as most of you know, that from around here, you know that the currents are very, very fast and challenging. The water is deep. Of course, there's this little bridge that was built in 1940, and we'll chat about that a bit. And then, of course, 1950, and then the most recent one. And the original bridge, which you may not have realized, this is the original bridge, completed June of 1940, commissioned, I think, July 1, 1940, was a 2-lane road. It had 2 lanes and a sidewalk on each side, and that was it. So really, the thought was, get rid of the ferries. You know, we need a bridge over to the west side of the Narrows to watch Gig Harbor and other communities grow. But it was felt at the time that a 2-lane road was just fine. Well, as it turns out, it really wasn't just fine. That's for sure. Also, there was a very interesting way that this bridge got designed. There was, as is so often the case, well, actually it's not much true anymore, but in those days there was a great deal of federal money involved in this. About half of the money was to come from the federal government, from a little agency called the Public Works Administration. And since they had control over half the money, they said, look, whatever design that the Washington Toll Bridge Authority comes up with, we'd like to have an independent assessment. And the bridge that was originally designed was done so here in the state, and it was a very traditional looking, it looked very much like the 1950 bridge. It had an open truss structure, which was somewhat stiffer than what ultimately got built. But it was still a 2-lane highway. It was still a 2-lane road. And so this review panel that was convened or requested by the federal government came up and they said, you know what, we can do this cheaper. And they did. They came up with another design. It's called a plate girder, which is what went into this thing. And it was cheaper. It also didn't hold up either, but hey. What Tacoma Narrows did for the engineering profession, it's a fair statement to say that it moved the state of the art and the state of the knowledge ahead by leaps and bounds. And sometimes that's what happens. You do that by failures, and that's what happened here. And so really, there was a lot of things not well understood about suspension bridges, but after that, this became, a lot of the basic principles became far more clear. The other thing about the bridge that you might not remember if you weren't around in those days, and I assume all of you weren't, it was a toll bridge. And again, half the money was going to be paid back by bonds, which essentially were done by tolls. Now, I don't expect you to read this. Not at all. I just put it in here to remind me to say something. There was the head of the Washington Toll Bridge Authority, and was essentially the head of what was then called the Washington Highway Department, or what would be called today the Washington State DOT, a gentleman by the name of Lacey V. Murrow. And he was the brother of Edward R. Murrow. And so many of you might remember him as a very famous newscaster from particularly the 1950s and 60s. That was his brother. And Lacey V., which we also had a bridge named after him that sunk, and I'm not trying to connect those two, I assure you. I quote from that article in the Seattle PI, just after the bridge opened to traffic. "I have heard reports that some persons have become ill on the bridge, but that is likely to happen on any high place. It's probably the height and not the motion that caused the illness." Well, that might have a little been an understatement on his part, as it turns out. Because a few short months later, 5 months later, the bridge collapsed. What you also might not have known is that there was quite a bit of work that got underway very quickly here at the University of Washington when the bridge, this excessive flexibility in the bridge was induced by wind, was certainly readily discovered. Actually, they begin to see this even during construction. There was some models that were built here on the campus affiliated with the Civil Engineering Department, and they were looking for solutions to quiet this dynamic situation down. They looked at putting holes in those plate girders and deflectors and so forth, and unfortunately, all this work was very much underway when the bridge failed. So there had been, some early remedial types of things that were tried, but for the most part, they never got to play that out fully. Now, this is a kind of an interesting shot of the roadway, and you can see that damaged plate girder there, and a couple of fellows over there walking down the cable, which makes, I'm sure, for a very interesting day. Another article, none of these, of course, I would expect you to be able to see, but the Seattle PI again in March 1941. This was after the bridge had failed. It was declared a total loss. The towers were actually twisted and damaged, and the cables were damaged, and so ultimately it was decided, look, we got to take the whole thing down. It's got to go. And so the narrow bridge to aid drive. Now, what does that mean? Well, it simply meant that folks were by this time, we were in World War II, fully engaged, and so every bit of scrap steel that could be salvaged out of the bridge was collected and recycled, essentially. And I'll show another image of that in just a second. This is one of the models that was built in the Civil Department to try to examine some of the remedial actions, and ultimately, actually, after the bridge failed, what kind of bridge should it be that we would build back? And of course, largely because of the war, the second bridge was not put back until 1950 or so. But anyway, all the cable, everything. I've heard all kinds of rumors about that the towers were shipped to some country and re-erected and stuff, and that's all nonsense. None of that's true. Everything was recycled to the extent possible. Although Steve's going to make an interesting side note about that when he starts talking. And they were removing the towers, and it said that this is the first big suspension bridge that was ever taken down. So, and it was kind of a challenging assignment in itself. Then the replacement bridge that came back, and you see that there's a truss structure underneath the roadway. They came back with a wider structure, which was felt to be more stable. And they also realized that in 5 months that the first bridge was actually under traffic, the traffic increased almost 150%. Now, hopefully that'll make you feel better as you go home tonight. And so they realized, look, we need more lanes. So when the bridge went back, it went back as a 4-lane highway. And the second bridge cost about $18 million. The first bridge, $6.4 million. And Steve will tell you what the third one cost. There's been a little inflation, as you might know. Now look, Steve's going to come up. He's going to get going. But this image simply says, he's affiliated with a company that knows bridges. This company has, and we only showed some of the significant bridges in the state of Washington. But these are bridges built by this company that this individual represents. And you can see the Tri-Cities Cable Stayed Bridge. They're redoing the half of the Hood Canal Bridge. That's underway right now. The West Seattle Bridge, Sela Creek Bridge over near Yakima. That's just to show a few. And so this company knows bridges. And they're doing some very, very big projects. I think you just finished the Benicia Bridge, didn't you? Isn't that that's pretty much done in the Bay Area. And they also built the Skyway portion of the San Francisco-Oakland Bay Bridge, which is almost finished, and there's another span that has to be built to connect it to Treasure Island. That's not quite done. I don't think that's your contract, is it, Steve? Anyway, so this company knows bridges. That's for sure. With that, I've introduced him. This is your main speaker, and I'm sure you're going to enjoy this. Steve Hansen. Yes, sir.
Good evening. As Joe told you, I'm Steve Hansen, and it's my privilege to tell you about the construction of the new Tacoma Narrows Bridge. As Joe said, this was an exciting, challenging, interesting. I could go on and on about the different adjectives that describe this project, and it is an exciting project. But what I'd really like to try to relate to you here today is the breadth of the engineering and planning work that goes into both the design and construction of a world-class structure like the Tacoma Narrows Bridge. This project was initially conceived as a private-public partnership back in 1994. Over the next 8 years, and a number of starts and stops later, it evolved into a design-build project. On July 16th of 2002, the state of Washington signed a contract with Tacoma Narrows contractors to design and build this project. 5 years and 3.5 million man-hours later, it was open to the public in July of 2007. After the contract was signed, we had a 2-month period of time to mobilize our people and get to the site. And then notice to proceed was issued on September 25th of 2002, and we were off to the races. The main parties involved in this project, the owner, Washington Department of Transportation, the design-build contractor called Tacoma Narrows Construction, which basically is a joint venture of the Bechtel Corporation and the Kiewit Corporation, and then our lead designers, Parsons and HNTB, were also a joint venture. Let's start with an overview of the major elements of the structure. In this profile of the bridge, the anchorages are circled in red. Now, the anchorages are the workhorses of a suspension bridge. For a suspension bridge to do its job, the 2 massive concrete blocks are usually at the ends of it to hold the main cables, and they resist the tension or pull of the main cables and support the structure. Each block on this new Narrows Bridge weighed 81 million pounds, had 1 million pounds of reinforcing steel in it, and over 20,000 cubic yards of concrete in it. And this whole thing was buried in the ground about 60 feet. Now, 20,000 yards of concrete is enough concrete to cover a football field, end zones included, 15 foot deep. The second major feature are the foundations. And these are probably the physically most challenging part of the project. And they support the main towers and struts. These foundations are commonly called caissons due to the method we use for construction. The word caisson means box in French. And as you'll see later in the talk, it's a giant floating box for most of its life during construction. The third major feature we'll talk about are the towers and struts. Now, the towers and struts rise up a dramatic 510 feet above the water level. And to put this size in perspective, if you take the towers and the caissons together, and you can see what they look like next to the Space Needle. So a pretty massive structure. The fourth major feature of a suspension bridge are the suspension cables themselves. They span from one end anchorage over the tower tops into the other end anchorage. And the purpose for the suspension cables is to support the roadway deck and the vehicles, of course, that travel on it. Each completed cable is 20.5 inches in diameter and is made up of over 8,000 individual wires, like the one Joe showed you earlier. Each of these wires is laid parallel to one another during the construction stage. And the final major element is a suspended roadway. It's shown here with several of the deck units being erected. Eventually, they make up a continuous 5,400-foot-long roadway section for the vehicles to drive on. Now that you've seen how each of the major elements fits into the overall structure, we'll step back and kind of walk through a number of these elements in more detail and kind of give you a detailed look into the planning and engineering that goes into the construction of a project like this. Starting with the foundations for the main towers, we had to develop a method to build a concrete structure that's 210 foot tall in 150 feet of swiftly moving water. We studied numerous options, and finally we settled on the one called the caisson method. And in this method, we developed a floating concrete structure that we added to incrementally as it floated. As additional concrete was poured, the structure got taller and taller, and as it got taller and taller, it sank closer and closer to the seabed. The engineering challenges we had here were twofold. First of all, we had to figure out how to maintain positive buoyancy, that is, keep its head above water while we were building it. And secondly, we had to figure out how to anchor it in the Narrows while it was being constructed. This video clip will show you the general sequence of construction. So what you see here is the caisson being constructed incrementally as it's floating. You're looking at the bottom of it right now. And as we add concrete to the top, it sinks deeper and deeper in the water. And you can see the anchor system that you were asking about being attached here to hold the thing in position. This isometric view shows the general configuration of the caissons. The caissons have a footprint of 130 feet by 80 feet, and they're 210 foot tall. This picture shows a cutting edge under fabrication at Todd Shipyards. The cutting edge gets its name from the shape of the outer edges that were designed to cut into the soil at the sea bottom during the excavation stage, which we'll see later. So as it sinks to the bottom, it actually cuts into the soil with the weight of the structure. At this stage, we're basically building a barge. There are 15 shafts that are hollow through the caisson from the top to the bottom. We temporarily covered these shafts with false bottoms at the top of the cutting edges to float the structure. That's the red tanks. You might note that the main members of the cutting edge are hollow, right there. This part of the cutting edge will be filled with concrete on the next stage. This cutting edge with its false bottoms in place was completed and launched just 6 months after notice to proceed. And we were quite excited to find that 750 tons of steel does float as planned. The cutting shoes were towed from Todd Shipyards in Seattle to our outfitting yard in the port of Tacoma. Now, the cutting edge itself was not intended to be tall enough to support the weight of the concrete required to fill its volume. It was built to basically be the first starter. And then we added 60 foot of steel skins at the shipyards in Tacoma. And these steel panels became the basic hull for the caisson during the rest of its floating cycle, initial floating stages. At the outfitting yard, we added the steel skin, started the concrete work, and did as much preparatory work as we could prior to being towed out and anchored at the job site. Here's the caisson being positioned at the job site. The crews are about to begin attaching anchors here and anchoring the caisson on location at the job. And here we're anchored up next to the existing bridge. We continued to form and pour the concrete incrementally against the steel skin. And as we're doing that, the structure drops lower and lower into the water as it gets heavier and heavier with more concrete. Eventually, we were able to use more conventional form process for the last 132 foot of the caisson, and we would pour the concrete in 10-foot lifts, the outer walls first, 4 foot thick, and then as flotation allowed, we would fill in with the dredge wells. And now this next video you're going to see why the anchor system had to be so massive. What you see here is one of our derrick barges being buffeted by about a 7.3 knot current flowing through the construction site. And here's the caisson itself anchored up. And the currents you see here, it's pretty much a maximum tide, are acted against the caisson as the tide's coming in. On the reverse tide, we'd have the same types of forces acting on the structure coming from the other direction. So that's what we had to deal with. Now we knew proper anchorage was going to be a major risk in the construction of the caissons, keeping that in place. Before we could engineer an anchor system, we had to understand what forces would be acting on the floating caisson. We used two processes to predict the load that we would see. The first was a numerical analysis using a finite element form of computational fluid dynamics, referred to as a CFD model. And this model required relatively massive amounts of computer inputs and computations to predict the forces. Here's another shot of a static shot of the model showing the ebb currents on the new and existing bridge piers. We supplemented the computer model analysis with a physical model test. We simulated the bottom of the Narrows in a laboratory in a Wallingford laboratory near London, England. And in this picture, you can see a bunch of wires. Those are the anchor lines. And they had strain gauges, and they were spread out as we intended to, as we proposed to use them. And the flows were put through the flume, and the forces were recorded. We added the derrick barges in the models as well to see if that had any effect on the currents or what the current did to our barges, because another concern we had is what are we going to have to do to anchor our equipment out here as well. So with these two sets of information, we went and engineered our anchor system. This is the plan view of our caisson with the anchor layouts. We did 2 rows of anchors, one at a 300-foot radius and one at a 600-foot radius. There's 16 anchors all the way around at each of those radiuses. Our anchor plan had to avoid the debris. Joe mentioned the stuff on the bottom of the Narrows. Well, the black dots are sonar shots. They're things like chunks of concrete, chain, etc. on the bottom. The black rectangles, those are big concrete blocks that the original contractor used to build the first foundation for the bridge. They're still there. And that area that's circled in red, the cross-hatched area, is a piece of the failed structure laying on the bottom. Now, all of those objects are part of a national historical site, and they weren't to be disturbed. So we had to build around them and not disturb them. So here's a cross-section of the caisson floating with a lower level of anchors installed. So when we brought the caisson to the site, we positioned it and hooked up the first row of anchors. The lower anchor, basically the predominant feature of it is a 4-inch steel chain, and you'll see that in a minute. And basically we use steel chain there on the bottom in case we did accidentally encounter something. We didn't want our cables rubbing against the thing on the bottom and parting our anchor cables. That could be disastrous. And then we anchored the caisson with what we developed a anchor system. It's basically the U.S. Navy has an anchor they call a toggle anchor they use. We made a massive one, a toggle anchor on steroids. And here it is. This is one of the anchors, and the 4-inch chain. Somebody asked me earlier, why is it 4-inch? That's the diameter of the part as it goes around. So, they're about 200 pounds. The anchor plate shown here was inserted vertically into the ocean bottom with high-pressure jet, a water jet, and a vibratory pile hammer about 30 to 50 feet. Then once it was down there, we test loaded them all, and as we put pressure on them, they would rise up and toggle, hence the name, kind of like an anchor in the wall, and that would mobilize the earth above it, and we'd develop a 500-ton anchor. The second anchor was installed at the 600-foot radius as the caisson advanced in depth. It used the same toggle anchor, but instead of the chain, we used a 3.5-inch bridge cable. Because again, the size of the materials we're using to anchor this caisson in place. As the caisson grew incrementally taller and taller, we adjusted the location of the upper anchor points with a sliding beam system so we could keep the spread between the anchors as much as possible. And this is the caisson just before touchdown on the bottom in 150 foot of water. Now let's look at what happens after touchdown. After the caisson touched down on the bottom, we flooded the interior structure with water and removed the false bottoms with divers. The false bottoms had done their job of keeping the caisson buoyant, but now that it was on the bottom, it was time for the next step in the process. So the divers cut out the steel bottoms. With the dredge wells now open, we began excavating, with a clamshell dredge. As we removed the material from below the caisson cutting edge, the weight of the concrete structure would cause it to sink into the seabed. We continued this process carefully, removing the material to allow the caisson to penetrate vertically into the design depth. Soil borings that we performed during the design stage were used to determine the final bearing elevation. The first caisson was completed 21 months after notice to proceed, and the second caisson, you can see it in the background there, was completed a month later. Tower construction could now begin. The next elements I'm going to talk about on the structure are the towers and struts. In this view, they're complete. The towers and struts themselves are reinforced concrete and have a hollow tapered cross-section. The width looking into the towers is 14 foot, that's constant. But the length or the depth of it tapers. At the base, it's 29 foot. As you get to the top of the towers, it's 19 foot. As you look at the towers themselves, you can also see that they're battered in. Our general superintendent had numerous visitors come into the job and asking him, "Do you know that the towers are leaning?" And he had explained over and over that everything was as planned, that the lean or batter was intentional. Now the batter was designed to allow the suspended deck to pass between the tower legs while you still keep the cables over the center of the towers where the saddles are. The batter also improves the lateral stability of the towers. Now, my wife tells me that she likes the batters because she thinks it makes the structure more attractive. Now, I think that's what Reggie should have told the visitors, don't you? As we planned the tower and strut construction, we schemed different ways to save time on the tower schedule. It became pretty clear to us as we were planning it that if we could figure out a way to build the tower legs without having to stop and build the struts during the cycle, but build them simultaneously as they pass by, that we could pick up about 3 months on the critical path of the job. And you can see in this arrow, we did it. That's the strut under construction while the tower legs are on up cantilever above it. Now this animation shows the towers being built using our self-climbing tower form system. The tower legs advance through the tower strut locations, and the struts are constructed off the critical path. We're getting up to about strut level now. It's going on by, and now we're starting, you can see the false work being erected, the strut being constructed, and towers are going on. I'd also like you to note how tall these towers are as the video closes above how much they're freestanding. One of the hurdles that we had from an engineering point of view to achieve the 3-month schedule savings was mitigating the wind effects on the unfinished towers. We were obviously very nervous about wind from the history of the structure, so we did some wind studies, and they were conducted by our designer in conjunction with a wind engineering firm in Canada. And that study showed that the towers could fail under certain wind conditions through wind-induced oscillations if we went on past the middle strut without waiting to build it. So after additional engineering, we came up with a scheme to add a temporary wind strut, which helped us to safely accelerate the schedule and save the time we were looking for. Now, the earlier animated video showed the overall tower leg construction sequence. Now I'd like to go into more detail really about how we built each lift of the structure. This outer white shell you see here, which we referred to as a bird cage, was installed around the actual form system. And basically it had two purposes. The primary one was to shield the workmen from the wind in the Narrows during the construction cycle. Especially as they get up quite high, it gets pretty nasty up there. But also it provided the extra benefit that they weren't having to look down the 500 feet all the time. They were enclosed. And access to this was provided by a construction elevator mounted on the caisson slab. And that provided access to the workmen up to the top level. They could get off on this birdcage level and go down inside the birdcage to the forms and do their work, or they could cross over a work bridge, and I'm sorry, they had to look down there, to the other tower. The next series of slides shows the steps in the construction of a typical tower lift. The sequence starts with all the preparatory work complete on a lift and the concrete being poured. And after about 12 hours, the concrete would set and become strong enough for us to remove the ties and roll back the forms. Then we could advance the self-rising or self-climbing mechanism, pin it off. Then we advance the outside forms. Then we'd hoist and set the reinforcing steel, get it all tied in place. Then we would reach inside and grab the inside form and hoist it with a tower crane. Then we'd roll the forms back in place, install the ties, and complete the cycle by pouring the concrete. It was typically done in about a 17-foot lift. To construct the tower, each leg was built in 28 individual pours. The sequence we just went through took an average of 7 days. We were, however, able to achieve a 4-day cycle about 25% of the time. The first tower was completed 34 months after notice to proceed, the second a month later. Now, as the towers topped off, we were able to begin the preparatory work for the caisson cables. The cable on the 3 spans of the bridge profiles to a length of over 5,700 feet. Each cable has 8,816 individual wires, 5 millimeters in diameter, this one here. And in total, there's over 19,000 miles of that wire in this structure. Approximately 5,500 tons of wire was required to construct the 2 main cables. Now, like each of the other elements of the project, the installation of the suspension cables took a tremendous amount of engineering planning, and I'd like to go through some of that with you. First, we're going to go through some of the preparatory activities. Then we'll show you the equipment involved. And then finally, we'll go through the actual construction of the cables, which we call spinning. Now, preparation for the main cable spinning included the installation of the catwalk, erection of the temporary tower top works, installing the permanent saddles, setting up all the erection equipment, and setting up a tram system to haul the spinning wheel back and forth across the structure. All the planning and procurement for this work took over a year. And during that time, our construction staff took these engineering packages shown and developed about 40 work packages to actually go out and build the work in the field. And that's just for the temporary construction I'm going to show you. And they had to develop a similar amount of packages to take all this stuff down when we were done. In all, about 25,000 man-hours was expended in planning and procurement for the pre-spinning activities. To help plan all the temporary works necessary for the cable spinning operations, we built a large-scale physical model. This model was invaluable in finalizing the detailed work plans to erect the catwalk and spinning operations. It's a great way to help communicate to the people involved. So our workmen, our supervisors, and the many visitors we had, we could explain how everything was going to work. Here's a picture of the model on one side and the actual in-place temporary works on the other there. And you note in the scale, inside that little red circle, there's two people working. The top works provided anchorages for the catwalk and catwalk strands, which in turn supported the side and floor mesh. And then it also provided places for all the blocks and running blocks and shifts to be attached for the tram system. You'll see in a video in a little bit showing the tram working. This is a close-up of the catwalk. Basically, the catwalk is to provide man access the full length of the cable. The rest of this equipment you see here is used to spin the suspension cables. And it could give you an appreciation for the amount of just temporary work that was required before you could actually start spinning the cables. This temporary work took 2.5 months and was completed on month 37 after notice to proceed. Now I'd like to talk about the spinning equipment. It's quite a bit of it. It started arriving in early 2005. We had 8 wire unreelers. These unreelers, each one would hold 24 miles of wire. And they would rotate at speeds up to 125 RPMs and could let out wire at about 2,000 feet per minute. The wire traveled from the unreelers and passed through these horizontal shivs and the automatic spray paint system here. We use fast drying highway paint shot on the cables about every 20 feet to help us locate and index the wires during profiling and adjusting of the cables under construction. From here, the wires would go through a floating shift tower. Basically, this tower was designed to keep the wires in a constant tension as the wheels accelerated, spinning wheels either accelerated or decelerated during the time that the spinning wheel was going across the structure. Now, all of this equipment, we had a control center, had a software controlled both the equipment speed and tension of the wire during all of the time it was pulled across the bridge. This control panel was operated by the tram dispatcher. Now there's 2 spinning wheels during the spinning cycle. One's on the east side of the structure, one on the west side, and they basically will go all the way across, pass in the middle, back and forth, back and forth. And that's basically where the name spinning comes from. It looks like spinning wheels. Now you're going to see an animation of the actual process here. Here's a spinning wheel, and the animation is showing taking some strands back and hooking them over the anchor shoe. And then the spinning wheel would go follow up the tram. The tram would pull it up the catwalk, up and over the structure to the other side, and then cross back. As I said earlier, there are two spinning wheels starting one on each end. They pass each other in midsection, shown here. Each pass of the spinning wheel would deposit 4 wires going out and 4 wires returning. Each trip, you get 8 wires. The main cable itself was made up of 19 bundles of wire. They're called strands. And each one of these strands has 464 individual wires in it. If you're doing the math, that's where you get the 8,816 individual wires for each cable. This is the first strand complete for the south cable. You can see the nice access on the catwalk there. After a strand was completed, we'd compact the 464 wires into a nice round circle, and then we'd band it to hold its shape. And here you can see the paint, and also you can notice the nice parallel nature of all the wires here. And here's 19 of the strands complete, so we're complete on one of the cables. Again, you can see the parallel nature of the wires. After all the strands were completed, they were compacted into a single round cable. So here's the 19 strands. We compact them to a single cable, shown there. To do the compaction, we had this giant cable compaction machine. Actually, we had 4 of them. And they squeezed it into a 20 1/2 inch round shape. And again, we banded it after it was compacted to hold the shape. And this is another view of the compacted cable with the compaction complete about halfway down the side span towards the anchorage. At the anchorage of the main cable, the cable would come in on the left here. The 19 strands would flare out, and they'd be further divided and hooked over the strand shoes. And then the strand shoes and the threaded anchors themselves were used to transfer the cable loads into the concrete anchorages. So now we've got the load transferred into the concrete and the cable's complete. Now let's take a look at the spinning in real life. We start off with the wire being transferred from the spools that they arrived at the job site on to the reels I told you earlier. So they're reeling them up here, making 24 miles of them. The reels went into the unreeler. Now you can see the fellow's putting one of the anchor shoes on one of the rods in the anchorage. A number of the strands are complete here. Now you see them pulling the cables back. Every cycle they'd bring the 4 wires back and hook them over the end shoe. Once that was done, the spinning wheel would take off from the anchorage. It's going over the saddle at the anchorage, and then it would head up to the tower top. Take about 12 minutes on a good cycle to make a complete cycle here of these 8 wires. Once it got to the tower top, the workman at the top would carefully position the wires in their predetermined position. Each of the 8,000 plus wires had a planned position that it went in, build them in a certain order. Lots of man hours of work here. Now the cable and deck work were completed, the cable work was completed 43 months after notice to proceed, and we were ready to move on to the next operation. Between the cable spinning completion and the deck erection, we had a number of operations. We had to install cable bands, cable suspenders, then we had to assemble and test our erection gantries. Now I'm going to skip over those activities and go into the last major element of the structure that I'm going to cover. That's the erection of the prefabricated road deck sections. Now deck erection is a very interesting operation due to the fact that the bridge is constantly moving. The towers deflect, the cables sag, the bridge deck sections move, all of those in reaction to the loads that you're inducing into the structure as you do the erection. Constantly moving structure. One of the factors that had to be analyzed for every phase of the segment erection was tower deflection. Our maximum allowed tower deflection was limited to 30 inches measured at the top of the tower. This animation just demonstrates tower deflection. You can see how placing too much weight causes the towers to over-deflect. Too much tower deflection is obviously unacceptable. An erection sequence was developed to minimize this deflection. We used 4 erection fronts with 4 separate erection gantries, so we could work on those 4 fronts. Now this simulation shows you the actual initial stages that we actually erected. And you can see we erect in a balanced manner to minimize the forces in the towers. The side spans, you can see some of the segments are actually moving horizontally. That's what we call trapezing, and I'll cover that later. Let's back up now and talk about the deck segments themselves. These were fabricated in South Korea by Samsung Heavy Industries. After fabrication, the deck units made the journey nearly 20 days from South Korea to Gig Harbor, Washington. And these ships are nearly 600 foot long and they have a 25,000 ton capacity. So they made pretty light work of our segments. And they hauled them across the Pacific Ocean to Gig Harbor. And once they got to Gig Harbor, they were towed to and tied up under the west side span of the existing bridge, where we had pre-installed some more of those toggle anchors you saw earlier to locate the ship. And all the segments were unloaded from all 3 ships at that location. Now they were handled differently depending on where their final location in the structure was. The ones that went on the west side span were hoisted directly off the ship to the road deck itself. But on the east span and mid span, the segments had to be unloaded from the ship onto a barge and then transferred to that location and then erected. To transship a segment from the ship to the barge, we utilized 4 winches that were mounted to the west tower. The winch line was routed along the main cable through a series of blocks and shivs and eventually connected to 2 lifting beams. From there, we hung some pennants down and hooked them to the segment and hoisted them. One of the special pieces of equipment that was developed for the job was the dynamic positioning barge. Imagine trying to hold a barge in place out there in the currents. You've got 4-foot swells, 30-mile-an-hour winds, and tides up to 7 knots. These were the kind of conditions we were trying to develop this barge to handle. In the end, a self-propulsion system was designed to safely maintain the barge on location in up to 3 knots of current. That's what we decided for a working condition. The heart of the barge's capabilities stem from 4 thrusters that were mounted, 1 on each corner of the barge. These thrusters are the largest of their kind in the world. Each thruster resembles a huge outboard motor engine and has 360-degree rotation capabilities. Once we had the barge assembled, we took it out and did physical sea trials to see what we could do. And we confirmed that it could actually hold its position at up to 5 knots in the Narrows, but we backed off to 3 knots to give us a factor of safety and to ensure that we could keep the barge within 1 meter during the hoisting process out there on site. In addition to the thruster power, at the rear of the barge, we mated it with a 4,400 horsepower tug. Now this tug was primarily just an insurance policy in case something happened during the lifting. If one of the thrusters would fail, we wouldn't have a disaster. Thankfully, we never had to fall back on that. The thrusters were operated through a computer program that utilized 3 independent survey systems. We had a GPS system, an optical system, and a radar system that told us the position of the barge. This provided sufficient redundancy to safely complete the operation even if one of the 3 survey systems failed, which it did on more than 1 occasion. So we were glad we had multiple systems. To lift the main span segments of the bridge, we used 2 of these gantries to hoist the segments with a hydraulic strand jack system. So we have 2 of these gantry systems for every hoist. We use these strand jacks, there's the strands, and those were connected down below to a lifting beam shown in yellow. And in this picture, you actually see the beam attached, and we're in the process of hoisting a bridge segment. Looks to be the first one. Now let's put it all together. Making a successful lift required good planning and coordination. A key component in our planning and coordination was our lift hourly schedule. This was simply an hourly schedule of every step that we had to go through to make a lift. This schedule took into consideration such elements as tides, the speed of the currents, gantry lifting speed, daylight hours, and so on. This schedule also provided a go or no-go decision on whether or not we'd go for the lift on that day. If we weren't ready, we wouldn't go. Now, missing the slack water window on one lift meant losing a day on the job schedule. In addition to this hourly schedule, we had our share of checklists. Once all the checks were completed, the deck unit was lifted with the gantries, moved under the gantries, the lifting beams were lowered, hooked up to the segment, and hoisted. And when we lifted it up off the barge, we did it in 4 stages to ensure a safe lift. We could perform visual checks at each of the stages to make sure that the lifting lugs were engaging properly and that the gantries each had the load distributed to them properly. Once we were assured of that, the operators would lift it up, we'd clear the barge, and we'd pull the barge out of the way. This is a time-lapse video showing a lift on the main span. I'm going to show that video again, and this time I'd like you to make note of the movement in the suspension cable as the load of the segment is applied. Now let's talk about what's one of the more interesting operations. It's deck trapezing. Deck trapezing is basically swinging a segment from one position to another in order to move the segment horizontally. This operation was necessary when we couldn't get the barge with the segment underneath where we wanted to go. The shallow water, up the slopes, and through the actual piers of the bridge themselves, you can't get a barge underneath the load, or the final position. So we'd hoist it up and then we'd swing it like Tarzan from location to location. So I'm going to run you through about 3 versions of this. Here are the gantries, and the gantry lines are shown in yellow, and the temporary hangers are shown in some version of red. And the segment needs to get where it's at, all the way across to the left where the anchorage is. The gantries lower the segment, causing it to swing and be supported by the temporary hangers. Then the gantries move down the hill, and you repeat the process. Here it is in real life. Isn't that a beautiful scenery there? Okay, here's a time lapse of some actual trapezing. So this is real life, and you notice how many days and nights this operation is going on. It took a number of days to move these segments from their hoisting location back to the abutment at the anchorage. Now, deck erection was complete 52 months after notice to proceed. The next 6 months saw a flurry of finish activities, and on July 15th, 2007, the bridge was dedicated and opened to the public. I'd like to take this opportunity to thank all the men and women who worked so many long days and nights to build this beautiful structure so that it's now being enjoyed by the traveling public here in this area. Thanks to all the engineering professionals, construction professionals, and the many craftsmen whose hard work made this possible and made it possible for me to show this to you tonight. I'd also like to make a special thanks to the State of Washington Department of Transportation They saw this project through for 13 years from the time it was first legislated that we could do it and today. So thanks very much.